Find the equation of the oblique asymptote for the function rah rah rah. Okay, so oblique asymptotes are also known as slant asymptotes. They do the same thing that a horizontal asymptote does, except they aren't flat. They are off at some kind of angle like this, and there's a line equation attached to them that we'll see in a little while. But first, if you have a rational expression like this, it is pretty near impossible to see what the oblique asymptote is in an expression like this. But you can tell when you're going to get one, and you will get one anytime the degree of your numerator is one more than the degree of your denominator. If your numerator is your denominator degree plus 1, then you will get an oblique asymptote. So here we have degree 2 up top, degree 1 underneath. That's the condition we need to get an oblique asymptote or a slant asymptote. How do we find them? Well, this form is not much help. What we need to do to reveal it is long division. This means 3x squared minus 2x plus 1 divided by x plus 2, and we know how to do polynomial division. Or if you've forgotten, prepare to be refreshed. It goes like this. We say x goes into 3x squared how many times? 3x times. Now we take 3x and multiply it by both of these terms. 3x times x gives 3x squared. 3x times 2 gives 6x. And now, just like in regular long division, we subtract. 3x squared minus 3x squared, gone. Negative 2x minus 6x gives negative 8x. Now, if we were doing this with numbers, we would now bring down another digit and start the cycle again. In this case, you bring down another term and start the cycle again. X goes into negative 8x, negative 8 times. Negative 8 times x is that. Negative 8 times 2 is negative 16. And again, we subtract. Negative 8x minus negative 8x is like negative 8 plus 8. That cancels. And then we get 1 minus negative 16, which is like 1 plus 16, which is 17. Okay. That's the long division done. And what it tells us is this f of x is equivalent to 3x minus 8 plus 17 over x plus 2. As in, the 17 is a thing that we should be dividing by x plus 2, except we can't because x won't go into 17. So this, in the box, is just a reinterpreted version of our f of x. They are exactly equivalent, but this form is going to help us a lot more than the previous form did. And here's why. You remember when we talked about horizontal asymptotes, we said anytime you have a number over x, any power of x, when x gets very big, this whole term vanishes. Well, that's still true. And that means if we do the limit as x goes to infinity of 3x minus 8 plus 17 over x plus 2, when x gets very, very big, this becomes very big. 17 divided by very big becomes negligibly small. This whole term vanishes. And that means as x gets very big, this function starts to behave like 3x minus 8. This is the only part that survives. And so we can say when x goes to infinity, when x becomes very large, our function f of x starts to behave more and more like 3x minus 8. The difference between this function and 3x minus 8 is this piece, and this becomes smaller and smaller and smaller until you can't even see it anymore. So that means if you're drawing the graph of this thing, one, two, three, four, five, six, seven, 8. There's our y. There's the y-intercept of 3x minus 8. Its slope is 3, so up 3 over 1. That, let's go different color. That line is our oblique asymptote. And, well, when x is small, the function may do all kinds of bopping around. It will eventually come up and catch up to that slant asymptote and begin to follow it very carefully. And it'll follow it closer and closer as x gets bigger. And the same thing on the other side. This function will eventually come down to that asymptote and follow it. In the middle, it can do all kinds of strange and wonderful things that may have nothing to do with this asymptote. It may cross it, it may ignore it, but the bigger x gets, the closer the function will get to this line. So the equation of the oblique asymptote is y equals 3x minus 8.